Welcome back, ladies and gentlemen, to section 6.5. We're talking day 3 now, and that means we're going to be calculating powers of complex numbers. Alright, so now to get the basic concept of how this is going to work, I'm going to kind of do something kind of generically here. Okay, now if I just have, again, a generic z, and I want it to be this, which is the standard form, I want to determine z squared. Okay, well, of course, z squared is like saying z times z, so that's like saying r cosine theta, and actually, if you don't mind, I'm just going to go cis, r cis theta times r cis theta. Okay, well, in order to do that, of course, I have this big string of multiplication right now, so I'm just going to rearrange it, and I'm going to rearrange it so I put the r's right next to each other, and then I'm going to put the cis's next to each other, so cis theta times cis theta, and, well, r times r, I'm pretty sure that's r squared, and then cosine plus I sine theta, cosine plus I sine theta. Well, again, if I'm multiplying, all I have to do is multiply the front numbers, which are technically 1s right now, so I'm not going to worry about that. But then what I do from there is add my angles, so it's theta plus theta. And again, referencing my calculator, I quickly discover that theta plus theta is 2 theta. Alright, so, let's see, z squared gives us something that looks like that. Interesting. Alright, so let's use that result to determine z to the third. Okay, now hopefully you've kind of already got this figured out, but just for the argument's sake, let's say z to the first times z squared now is going to be r times cis theta, so that's my z to the first, and z to the second we just figured out is r squared cis 2 theta. Okay, now doing the same basic logical argument here, I get my r and my r squared. That's going to give me r to the third, and then I'm going to add my thetas again, or my angles. In this case, I get a theta and a 2 theta, and I'm pretty sure that if I take theta plus 2 theta, I get 3 theta. Alright, so hopefully if you didn't see the pattern already, you kind of see it now. Okay, now, a long time ago, a French mathematician named De Moivre figured this little pattern out using the trigonometric forms. And so I've got z, if I got this, z to the n, all I have to do, if I have the trig form, is take that r value to the n, and then all I have to do, and I'm going to write it out kind of longhand now, take the cosine, again notice whatever power I use, that's the coefficient of my theta. So cosine of n theta plus I sine, again, of n theta. So it's a nice little trick where you can easily take powers of complex numbers, at least as long as you have them in the trigonometric form. So slick little formula, and it comes in very handy. Alrighty, so I'm just going to put a few of these examples to the test here. Alright, so if I'm going to write 2 cis pi over 3, and I've got that to the fifth, I want to put that in the standard form. Okay, now notice I do want standard form here, so the trig form is going to come very, very quickly, but then we're going to have to convert it from the trig form that we have into standard form. So let's go from here. Alright, so again, there's my number. I'm taking it to the 5th power, so basically what this guy is going to equal is, again, my r value in the case of 2 to the 5th, and then again, using my cis notation, just because I'm lazy, is going to be 5 times pi over 3. Okay, now cleaning this guy up a little bit, I get 32, 2 to the 5th, and then cis, and that's a little bit nicer, 5 pi over 3, if I write it that way. Okay, and really, if I was just asking for the trig form, I'd be done right now. So, right there is the simplified trig form of this guy to the 5th power. Okay, very nice and compact. Okay, but again, I wanted standard form. So, what I'm going to have to do is kind of imagine myself again, using my unit circle. Okay, 5 pi over 3, and it puts me down here in the 3rd quadrant. And that's a little sloppy right there, but puts me at a 1/2 and then negative root 3 over 2. Okay, now again, remember, again, just for the sake of writing it out neatly, this is really cosine of 5 pi over 3 plus I times sine of 5 pi over 3. Okay, so leave my 32 there for just a minute. Now the cosine of 5 pi over 3 is my 1/2, plus I times the sine is going to be the negative root 3 over 2. And basically all I have to do now is distribute my 32. 32 times 1/2 is 16, and then 32 cancels the 2 down to 16 again, and I've got this negative root 3 along for the ride. So basically what I get is negative 16 And then, I don't know, up to you to decide what to do with the I versus the radical. Sometimes I think it's a little awkward to have the I after the radical. Again, that's why I like that little notch there, showing them closing 3. If you put the I between the 16 and the root 3, I wouldn't hold that against you. It's just a little easier to see what's going on that way sometimes, but whatever the case, that would be then the standard form. And again, that would be a heck of a lot nicer than trying to write this thing 5 times and do a whole bunch of FOIL sort of things. Okay, another example right here real quick, and this one, okay, so I've got the third power, and I've got it in standard form already, so I'm going to go from standard form to standard form, but I'm going to kind of go through trig form to do it. Although admittedly, writing this guy 3 times and doing the FOIL wouldn't be the end of the world. But just to show the usefulness of this without getting numbers that get too far out of control, here we go. Okay, first of all, I want to turn this guy into trig form. Okay, so that being said, again, I want to kind of imagine this thing visually. So I've got -4 and then +4, and again, hopefully not too hard to figure out there that I'm dealing with a 135-degree angle or a 3 pi over 4, whichever your brain likes better. Okay, but point being, this is -4, this is +4, and then my hypotenuse that I made kind of hard to see right now is going to be 4 root 2. Okay, and again, that's my R value. And again, whichever one of these you want to use, I'll probably actually just use the radians here, but here we go. Alright, so now this guy in trig form is 4 root 2, and then again, cis 3 pi over 4. But again, I want to take this guy to the third power, so I'll just throw this guy in some parentheses, put a little 3 up there. Okay, so I've got to take 4 root 2 to the third power. So basically this is one of those deals, if you're going to type that in a calculator, be very careful as you do it, because it's really easy to mess that up and get the wrong answer if you're not careful. Okay, that being said, I'm moving on to my cis. Now I've got cis of 3 times 3 pi over 4. Okay, I'll throw that in parentheses for clarity's sake. Alright, so basically right now I've got 4 to the third, which is 64. I'm going to do this a little bit off to the side here. That's what I get from the 4 to the third, but now I've got root 2 to the third as well, and root to the third is kind of a root 8. Well, not kind of, exactly root 8, which simplifies to 2 root 2, so the 2 gets together with the 64, making a 128, with a root 2 kind of left over. Okay, so that's cubing that guy, and again, if you're typing that in the calculator, be careful. It's easy to mistype something, so double check you know how to do that properly, please. Alright, moving on, we've got the cis, and then basically all I get here is a 9 pi over 4. Okay, and something might be going off your head right now, like, wait a minute, something's up there, because 9 pi over 4 is actually bigger than 2 pi. So if you'd like, what we can do is say, well, 9 pi over 4 minus 2 pi, or better yet, 8 pi over 4, is going to be a single pi over 4. So if you'd like to do that conversion anytime you get something bigger than 2 pi, that's probably not a bad idea. Okay, so what I'm looking at is 128 root 2 cis, basically pi over 4. And again, pi over 4 is a nice handy value to work with because it's simply root 2 over 2 twice. Alright, so there's my order of pair there. Okay, so again, doing my conversion, I've got 128 root 2. Okay, now my cosine is root 2 over 2 plus I times sine, which is conveniently also root 2 over 2. And again, we're just going to distribute. Okay, this one actually works out in a very, very handy way because the root 2 hits the root 2 here, becoming a 2, reducing with the 2 that's already there, leaving us with a 128. Plus, and then the same thing happens here. The root 2 and all that stuff cancels like we just had a second ago, so we get 128i. So then there's the standard form, again going through the trig form, and admittedly you might look at that and think, well heck, I would have just rather cubed this thing using FOIL, but again, that's just demonstrating how the trick works. If this was a 7th power, you probably wouldn't want to FOIL 7 of those together, and this would be a better approach. But anyway, there you go. Alright, let's do one more, just because. What happens if we don't have things that are nice unit circle-y sort of ratios? And that's exactly what we have here. 1 plus 3i to the 6th, although the 6th is irrelevant as far as determining whether we have a unit circle value or not, and we certainly here don't. Alright, so just kind of off to the side here, I'm going to draw what I have. 1 plus 3i gives me something that looks vaguely like this. So there's my 1, there's my 3. And again, here, I'll just throw theta in there. Okay, Pythagoras gives me right here a root 10. Alright, so going to trig form now, Okay, what I've got here is that this guy equals root 10, and then I've got a problem here because I've got this theta that isn't a nice value, so basically I'll just use an inverse trig sort of thing. The good news is, yeah, I can either use radians or degrees, because basically what I'm going to do here is convert them into trig form and then go back to standard form. So regardless of which measure I choose to use, degrees versus radians, it's actually going to go away eventually anyway. So whatever works for you, I'm going to work it out in radians, but here we go. Okay, so basically to get theta, I need to do the inverse tangent of opposite over adjacent, so that's 3/1, and that gives me some icky decimal such as 1.249 ... forever. Okay, so basically there's my angle measure in radians. Again, I could have done degrees, but I chose to do radians. Okay, so I'm looking at cis of 1.249 icky. Okay, but remember, this thing is all going to the 6th power. Alright, so I've got to take root 10 to the 6th, and then cis of 6 times 1.249 icky decimal. Alright, root 10 to the 6th, hopefully you can actually do that in your head, because the root is like the 1/2 power, and the 1/2 to the 6th, you're actually taking it to the 6th power, but you're doing 1/2 times 6, which actually becomes a 3. And so basically what I end up with is 10 to the 3rd, which is 1,000. If you don't believe me, please type that in a calculator. Alright, and then I've got cis, and I don't expect to do that in your head. I can't do that in my head. And I get 7.494, again, icky decimals forever. Alright, so basically again there's my trig form. It's just a very messy trig form, and if that's where I wanted you to stop, I'd have to give you some direction about what angle measure to use and how to round it. Okay, but we're not stopping there. Alright, so 1,000, and just again for the sake of argument here, I'm going to write this guy out kind of longhand. So cosine of 7.494 icky decimal forever plus I sine 7.494 icky decimal forever. Alright, now admittedly here, since I'm using my calculator, I don't care right now that these are actually over 2 pi, because remember 2 pi would be 6.28-ish, so this is a little bit bigger, but the calculator doesn't care, so I'm not going to worry about converting it right now. Alright, it's just if I'm doing it by hand, I want nicer ones to work with, but the calculator doesn't care. Alright, in case you didn't notice, the calculator doesn't care. Alright, now the most amazing thing about what's about to happen is by properly leaving all these decimals in the calculator and not doing any sort of rounding ahead of time, when I take the cosine of that icky decimal, it gives me an exact decimal of 0.352. Alright, again, I'm not rounding there at all. That's exactly what that comes out to be. And honestly, it kind of seems amazing, although when you kind of think about it, it isn't as amazing, so don't think about it too much. I'm kidding. Okay, same thing here. When I do the sine of this icky decimal, I get 0.936. Again, exact decimal. Alright, so then distributing the 1,000, which is a pretty easy thing to do, gives me 352 plus 936i. Okay, now the reason why, again, initially that seems like such an amazing thing. Cosine of some icky decimal gives me exact decimal. Okay, cool, but if you think about what's actually happening, remember, we're foiling this thing right here. And if I were to do FOIL on this, I would never encounter any decimals whatsoever. So it kind of makes sense that through all this whole process, all the decimals eventually go away. Because if I would actually do this by FOIL, I would never see them anyway. Okay, hopefully that makes a little bit of sense. Okay, and here's our assignment. Okay, nothing too spectacular here, but otherwise, I'll see you in class.